After a detailed discussion of classical theory of paramagnetism, today we are going to start its quantum theory. Actually, you have seen in previous two videos the classical theory of paramagnetism. First of all, we have seen the Langevin theory, and after that you have seen a very short lecture on the modification of Langevin theory of paramagnetism due to Weiss. Okay. Now, our aim of today's lecture is to discuss the quantum theory of paramagnetism. Actually, when you want to understand the quantum theory of paramagnetism, you must have a knowledge of vector atom model in atomic and molecular physics. So I will suggest you, before watching this video, you must go through my video on vector atom model in atomic and molecular physics of my channel, and then you can understand this lecture very easily. Actually, when you will watch my video on vector atom model, particularly LS coupling, then you will see that I have discussed in very detail the space quantization of angular momentum vector. Whenever an atom is subjected to a magnetic field, actually the electronic orbit or the atom is space quantized. When you say that this is space quantized, that means the angular momentum vector has not all possible orientation but some selected orientation with respect to the magnetic field in space. Actually, that space quantization will be used in this quantum theory of paramagnetism. So I will suggest you go through my video on this subject in the playlist of atomic and molecular physics of my channel. Okay. Actually, when you talk about the classical theory, you have seen that in classical theory we have stated that any orientation of electronic orbits or atom with respect to the magnetic field direction is possible. It means in classical theory we do not talk about the space quantization of electronic orbit. But the actual situation is not like that. In fact, quantum theory contradicts this statement and suggests instead that there can be only certain permitted orientations of electronic orbits or atom. Okay. Actually, these allowed orientation of an atom when placed in a magnetic field with respect to the field are directed actually in some particular direction. As you can see this figure, here I have shown that this orbital angular momentum vector L, this precess around J, which is the total angular momentum vector. You know, the total angular momentum vector J is given by L plus S. This is called LS coupling. In fact, here this L is the orbital angular momentum vector and S is a spin angular momentum vector. And the vector sum of these two angular momenta gives the total angular momentum or the resultant angular momentum J. Actually, when an atom is placed in a magnetic field and the magnetic field is not very strong, actually in that case what happens? L and S both precess around its resultant J. Okay, and J itself precess around the magnetic field H. Have you understand? The precession of L takes place around J, and the precession of this S also takes place around J. But J itself precess around H, as I have shown in this figure. Okay. And the angle made by this vector J, you can see, with the magnetic field vector or its component in the direction of magnetic field vector, which is actually equal to mj, I have assumed theta. actually this theta has some particular values. Not all values of theta is possible. You can see from this figure that cos theta will be given by what? This will be given by mj divided by j. Okay, and mj and j both have actually discrete values. You know, j is the total quantum number, okay, and it has discrete values, and mj, which is actually the resultant magnetic quantum number, and the value of mj depends on the value of j. Okay, value of mj depends on value of j, and for a given value of j, mj has total 2j plus 1 values. All these things you can see in my video in atomic and molecular physics. And actually this mj has values from plus j to minus j. Total value is 2j plus 1 at a step of 1. So mj can assume the value j, j minus 1, j minus 2, and so on. And in this way the value will be 0, minus 1, minus 2, so on, minus j. Total 2j plus 1. Since mj has discrete values, so cos theta will have also discrete values. So you can say that the atom orient itself in the space in some particular direction, not in all possible directions. This is actually called the space quantization of atom in an external magnetic field. Okay. Now, as our aim is to discuss the theory of paramagnetism, so it is obvious that we have to find the magnetization and the susceptibility of the material. And for finding the magnetization and susceptibility, first of all we will find the magnetization, and after that you can find the magnetic susceptibility. Now let us see. This atom will have a component of magnetic moment parallel to H, and that will be equal to what? The magnetic moment of the atom parallel to this applied magnetic field vector H, that will be equal to G times mj times mu b. This formula you can learn in atomic and molecular physics. I have directly written it here. Actually, what is this G? G is called Land's splitting factor, you know. And mu b is a well-known constant which is called Bohr magneton. Okay. So the component of this the magnetic moment of the atom along this direction H, this is given by G times mj times mu b. Okay. Now once you know the magnetic moment in the direction of H, you can easily find what will be the magnetic potential or magnetic potential energy of the atom. Because you know, when an atom is when a magnetic dipole is subjected to an external magnetic field, the energy developed or the energy of interaction due to the magnetic interaction is given by minus mu dot H, where mu is the magnetic moment. Okay. And this will be equal to minus mu cos theta times H. You can treat this mu cos theta as the component of mu along the direction of H. Okay, along the direction of H. And so this can be written as minus mu H times H. Here actually mu H represents the component of magnetic moment in the direction of field vector H. But what is this mu H? You can see this mu H is equal to this much. This is G times mj times mu b. Okay. So in this way, substituting this value for mu h, you can easily find what will be the interaction energy of the atom or the atomic dipole when it is placed in the external magnetic field H. Actually, all these calculations I have made here, you can see that the allowed orientation of an atom when placed in a magnetic field with respect to the field direction are given by this. Okay. And as I have told you that this J is what? This is resultant angular momentum quantum number, and Mj is resultant magnetic quantum number. And as I have told you that for a given value of J, there are 2J plus 1 values of Mj. Actually, the values of Mj runs from plus J to minus J at a step of 1. Okay. So you can see that this Mj will be equal to what? This will be J minus 1, J minus 2, so on, 0, minus 1, minus 2, up to minus J. Okay. Total values are 2J plus 1. So actually in the space, there will be 2J plus 1 orientation of our atom. Okay. And all those orientations will be discrete. Okay. Now, let us see. As I have told you that the component of magnetic moment parallel to H, it is given by G times mu b times mj. Here G is length splitting factor, and you can see my video on length splitting factor in very detail in my playlist of channel named Atomic and Molecular Physics. So I have suggested you to watch those videos first of all. Okay. And mu b, this is the well-known constant which is actually called Bohr magneton, and it is given by Eh bar over 2m. Here h bar is the reduced Planck's constant. Okay. And m is mass of electron. And when you will substitute the numerical values of all these constants, you will see that its value is 9.27 times 10 to the power minus 24 ampere meter square. Okay. This is actually called Bohr magneton. Okay. Now, as I have told you that when the atom, when you say atom, that means atomic dipole, because you know the atoms of a paramagnet has permanent dipole moment, so they behave just like a magnetic dipole. And that dipole is interacted with the external magnetic field H, and due to that interaction, magnetic potential energy is developed in it. And that energy is given by this formula, as I have told you, and this is minus mu h cos theta, and this mu cos theta may be treated as the component of magnetic moment in the direction of H, and that is equal to G mu b times mj. Okay. So the interaction energy is E equal to minus G mu b mj times H. Okay. Actually, electrons are fermions. They obey actually the Fermi-Dirac statistics. But here, for a simple calculation, we have assumed that this electron gas obeys the Maxwell-Boltzmann distribution law. Although this is not strictly correct, but we can get an approximate result when we will use the Maxwell-Boltzmann distribution law for finding the number of atoms of the gas with quantum number mj. And you know, according to MB distribution law, the number of atoms having energy equal to E is proportional to this Boltzmann factor E to the power minus E over Kb times T. Okay. Here Kb is Boltzmann constant, you know. But here you can see, in present case, this energy E is equal to minus G mu b mj h. So when you will substitute this value, this minus will become plus, and you can say that N is proportional to this much. And you can also write that N is equal to some constant, let us say A, and E to the power G mu b times mj times h over kb times T. You can see. Okay. Now, our aim is to find the magnetization. And what is magnetization? You have already learned in my introductory lecture on magnetism. That magnetization is simply the induced dipole moment per unit volume of the specimen. Okay. So, if your aim is to find the magnetization, how you can find? If you know the number of atoms or number of, you can say, atomic dipoles in unit volume of the substance, and you also know the average value of magnetic moment of an atom, then by simply multiplying this number of atom, which is the number of atom in unit volume, to the magnetic moment of one atom, we will be able to find the magnetic moment of unit volume. And magnetic moment of unit volume is nothing, that is simply the magnetization. Okay. So let us try to find the average value of magnetic moment per atom and then multiply it by this n to get the magnetization. Have you understand or not? Definitely you have understand. So let us see. If m is the magnetization, that is magnetic moment per unit volume, then this m will be given by n times average magnetic moment per atom. Okay. And how we can find the average magnetic moment per atom? As you have seen, the number of atoms with energy, with energy this much, mj times mu b times g times h, okay, with minus sign, that number is equal to n. Okay. And so when we will multiply the magnetic moment, which is actually equal to mj mu b times g along the direction of magnetic field by this Boltzmann factor, and sum up for all possible values of mj from minus j to plus j, and divide it by the total number of atoms. Okay. Total number of, the total number of atoms will be what? There will be a constant here too, so you can write a constant here, but that constant will cancel, and total number will be given by sum of this factor. Okay. Because this n actually represents the number of atoms having this much energy, and so the total number will be sum of this, and the limit of summation will be from minus j to plus j, because we are summing over the all possible values of mj. Okay. So the magnetization will be given by this expression. I think we have understand. Okay. Now you can see the value of magnetization depends on two factors basically, as you have also seen in classical theory. The first factor is temperature T, and the another factor is the magnetizing field H. So the values of T and H determine the value of this magnetization. Okay. So basically we will consider two cases. And as I have told you that this is our first part of the lecture on quantum theory, because we will discuss only the first case in this lecture. The second case will be discussed in the subsequent second lecture, because when we will discuss the both cases in one lecture, that will be a very lengthy calculation and there will be a lot of time, and so I have divided the lecture in two parts. So in first part of this lecture we are going to see only the case 1. Okay. And in this case 1, I am considering that temperature T is very high, okay, and the field is small. Okay. T is high and H is small. So if you consider that temperature is very high and the applied field is small, In that condition, what will be this factor? You can see mj mu b gh divided by kbt, which is the power of exponential. You can see that will be actually much smaller than 1 because h is small and t is very large. So this will be much smaller than 1. And you know, when we expand e to the power x, then this is almost equal to 1 plus x in first approximation. When you consider that x is actually h is actually much smaller than 1. This is called first approximation. Actually, in this condition, all the terms containing higher power of x are neglected. So in this condition, since the power of exponential is much smaller than 1, you can see, so we can expand this exponential term up to the in first approximation. And so you can say that in this very condition, e to the power mj mu b gh over kt, this can be written as 1 plus mj mu b gh over kt. Okay. So if you want to find the value of this magnetization in this particular case, when we have assumed that temperature is high and field is small, then expand the exponential factors in this way. Okay. So you can see I have made that calculation that in this condition m will be given by ng mu b summation minus j2 plus j mj times 1 plus mj g mu b h over kbt. This has been written for the exponential factor in the numerator. Okay, and here mu b into g is actually a constant factor. It has no relation with the summation, so it has been taken outside of the summation, and n is already present. Similarly, in the denominator, the exponential factor will be replaced by this. You can see. Now you know, when we will sum up 1, here 1 is present. You can see. From minus j2 plus j, the sum will be equal to 2j plus 1. You can check it. And sum of mj, when mj runs from minus j2 plus j, that will be equal to 0. Because there will be equal values of mj which are plus and minus. So they will sum up to 0. And when you will sum up mj square from minus j2 plus j, your result will be this much. This is j times j plus 1 plus 2j plus 1 over 3. This is simple mathematics. You can do it. Okay. So now let us see. When we will apply actually these results here, what will be our result? You can see in the numerator there is mj times mj square. When you will multiply by this mj to 1, you will get mj, and the second term will contain mj square. You can see. But summation over mj is equal to 0, so the first term in numerator will become 0, and for mj square we will have to write this much. Okay, and in denominator there is 1 here, and sum of 1 you can see this is 2j plus 1. But in second term mj is present and sum of mj is 0, so in denominator this second term will become 0. Okay, so after this simplification, what is our result? You can see m will be equal to ng mu b times 0 plus g mu b h over kbt. G mu b h over kbt, see here, and summation over mj square. Here will be mj square, mj times mj, and that will be equal to this much. So this is j times j plus 1 plus times 2j plus 1 over 3. Okay, and in denominator sum of this 1 from minus j2 plus j, that will be actually equal to 2j plus 1, but in second term mj is present, so sum will be 0. So in denominator there is only 2j plus 1. Okay, Now you can see that this 2j plus 1 and this 2j plus 1 will cancel out, and your result will be m equal to n g square. Here is g and here is g, so there will be g square. Again, mu b times mu b will be mu b square times j into j plus 1 times h, and divided by 3 kBt. So this is the expression for the magnetization. Okay. Now once you have calculated the value of magnetization, you can easily find the value of paramagnetic susceptibility, because you know from the definition of susceptibility this is given by chi equal to m over h. So when you will divide this m by h, this h present here will cancel, and the remaining factor is this much, and this is the expression for chi. So chi is equal to Ng square mu b square times j plus 1 over 3 kBt. Okay. So in this way we have actually calculated the magnetization and the magnetic susceptibility for a paramagnetic material. Now you will see the result which we have obtained by using the vector atom model or quantum mechanical theory, how it differs from the classical result. Let us see. Actually, for convenience, you can write this equation 3 for the magnetic susceptibility in this way. Chi equal to n times mu j square over 3 kBt. You can see mu j square you have written for what? This has been written for g square times mu b square times j plus 1. Okay. So mu j square has been written for this. Okay. Or you can say that mu j has been written for g into mu b times root over j into j plus 1. Okay. Now remember, we have already studied the classical theory, that is the Langevin theory of paramagnetism, and you have seen according to classical Langevin theory, the magnetic susceptibility of a paramagnet chi is given by this formula. You have already learned. Okay, n mu square over 3 kBt. So when you will compare this result, let us say this is 4a. The result defined in 4a and this equation 4, you can see what is the basic difference. Actually, both equations are identical. Only difference is in the value of mu. Actually, at the place of mu, there is mu j in quantum mechanical theory. Okay. So you can say that quantum mechanical result defined in this equation 4 is quite similar to the classical result which I have defined here in equation 4a. The only difference is that in quantum result, mu j is replaces mu. Okay, this is the only difference. Actually, what is this mu j? Mu j is equal to, as you have seen here, this is g mu b times this much. And you can write it as P effective times mu b. Okay. So what is this P effective? P effective has been written for g times a square root of j times j plus 1. Actually, this is the effective number of Bohr magneton. This P effective, which is given by this is called effective number of Bohr magneton. Okay. So in fact, the result is completely same in form as we have learned in classical theory, but there is a difference in the value of mu. Instead of mu, here there is actually mu j, and that mu j differs from its classical value. Okay. Now you know, if you consider the ground state of the atom, actually in ground state, this orbital quantum number L is equal to 0. And if L is equal to 0, the total quantum number J will be equal to S, because J is equal to L plus S. This is also L plus minus S both. But when L is 0, then you have to take only plus sign. Okay. So J will be simply equal to S when L is equal to 0. This minus sign is not taken when L is 0. Then only you have to take plus sign, as you can see my video on this subject in atomic and molecular physics. Okay. So if you are considering the ground state of the atom, then the effective number of Bohr magneton denoted by the symbol P effective will be given by G times square root of S times S plus 1. J has been simply replaced by S plus 1. Okay. Now, the value of this P effective, which represents the effective number of Bohr magneton, actually this value is found quite true in case of monatomic gases. But this value does not fit in explaining the paramagnetism of transition elements. Okay. So there is something lacking in this theory, because this result is an appropriate result. It is in accordance with the experimental result for the monatomic gases. But when you talk about the transition elements, then this result does not fit into the experimental result. Okay. So actually, for removing this problem, a well-known scientist Van Vleck pointed out that the assumption for every particle to be in the same L, S and J state is not true. Okay. He dealt the problem with consideration of energy h nu required by the particle to excite to higher energy state. Okay. In fact, if you are considering the ground, this is ground state, okay, and these are the different excited states, then energy needed to bring an atom from ground state to its excited state, let us say 1, 2 or 3 and so on, the required energy is h nu. This is energy of the photon. When you will incident the photon on this atomic system, the atom gets excited by absorbing the energy h nu, and it may move to this excited state if appropriate amount of energy is absorbed by it. If h nu is sufficient to raise it to any excited state, then it is possible. Okay. So actually, considering this very fact, we can consider two cases. First of all, let us consider that this h nu, this is actually the excitation energy, is much greater than kb times T. Kb times T is what? This is actually the thermal energy of the atom. Okay. And h nu is the energy required to excite the atom from ground state to the any excited state. But our assumption is h nu is much greater than kbt. It means for excitation of atom, we need a much larger energy than this thermal energy. So in this condition, the particle will be not excited to its will not excite to the higher energy state, because the energy needed for its excitation is much greater than kBT. But in normal room temperature, its energy is of the order of kBT, and so the atoms will be most probably in the ground state. Okay. So I have written it here. You can see in this case nearly all the particles must be in their lowest state, that is ground state, and the probability of occupation of higher energy levels is small because of the fact that sufficiently high energy is required to raise them to the higher energy state. Okay. So in this case there is a possibility, a larger possibility of atom to remain in the ground state. Okay. So in this condition, chi will be defined by this result. You can see chi is given by this result. Okay, and this is the value of chi. Okay, and you can write this that this is equal to C over T, where C has been written for this Ng square mu b square J times J plus 1 over 3 kb. Actually, this is called Curie's constant. And you know, chi equal to C over T, this is nothing, this is simply Curie's law. So you can see that when the excitation energy is much larger, in that condition, it is strictly accurate and obeys Curie's law. This equation will be strictly accurate and it will obey Curie's law. That is, the paramagnetic susceptibility will be inversely proportional to absolute temperature T. Okay, and in this condition, the expression for the effective number of Bohr magneton will be given by this. Okay, but what will happen when you talk about h nu is much smaller than kBt? In this condition, even at room temperature, there will be a finite probability of excitation of atom, because the excitation energy is much smaller. So in this condition, there will be a larger probability of finding the atoms in excited states. Okay, so I have written that in this case particles exist in different energy states and probability of occupation of higher levels is greater. Okay, then what will happen actually in this case? Actually in this case, what will happen? For this, you have to see the situation which you have learnt in atomic and molecular physics if you have watched the Paschen-Back effect. Have you studied Paschen-Back effect? The idea of Paschen-Back effect will be then applied in this case. Actually, when the external magnetic field H, see here the first figure, you can see when this external magnetic field which is applied to magnetize the material, this becomes very stronger, or you can say that this is greater than as compared to the internal fields. Actually then the coupling between J and H exceeds between the coupling between the L and S, and the precession of J about H becomes faster and than that of L and S about J. So under these conditions, the coupling between L and S is partially broken and J is no longer fixed in magnitude. And in that condition, both L and S start precession about H independently. Have you understand? When H nu will be much smaller than kb times T, in that condition the coupling between L and S will be partially broken. And what will happen? In that condition, actually L and S will start precession about this magnetic field independently. Okay, actually this idea is used in Paschen-Back effect, which you can see in your course on atomic and molecular physics, and I have actually provided a video on this and you can watch that video. Okay, so actually in this condition, I have written it here, you can say, therefore Van Vleck argued that LS coupling is weakened and L and S precess individually around H, giving their individual contribution to the magnetic moment. And in this case, Mj is replaced by Ml plus 2Ms. Actually, why this 2Ms? Actually, the Lenz's splitting factor for orbital angular momentum is GL and that is equal to 1. But for a spin of electron, this length splitting factor is 2. So in this condition, Mj is not equal to Ml plus Ms, but this is equal to Ml plus 2Ms. Okay. So if now you want to find the expression for magnetization M, then you have to solve the it solve the equation 1 which have been written for M separately for Ml and Ms. Okay. So again let us see first of all the expression for see here. Actually you can see the equation 1 here. This is equation 1. And in this equation, Mj has been used. Okay. Instead of Mj, now what you will use? We will actually use now Ml plus 2Ms. So term for Ml and 2Ms will be written separately. And you can see I have written that expression in this case, and that you can easily understand. You can see this M will be then given by N times mu B summation Ml from minus L to plus L Ml times e to the power, sorry, this will be just okay. Let us see. Okay. E to the power Ml mu B H over KBT and over summation Ml from minus L to plus L e to the power Ml mu B H over KBT and plus now for you have to write for a spin part, and that will be summation Ms from minus S to plus S to Ms. Mark it. Due to for a spin this Gs is equal to 2 and e to the power 2Ms mu Bh over KBT and divided by summation Ms from minus S to plus S e to the power 2Ms mu Bh over KBT. Have you understand? This has been written. Now again we will expand the exponential factor under that condition that e to the power x is equal to 1 plus x when x is much smaller than 1. Under this assumption we will expand all the exponential terms. Okay. Now let us see. This m is n times mu b is at is. Okay. And here in numerator you can see for this exponential factor I have written this much. Okay. 1 plus x. And in denominator for exponential term this has been written. Okay. Similarly in second term there is 2ms and for exponential I have written this and in denominator this. Okay. Again you can see as you have learned for mj, you know the sum of ml for from minus L to plus L that will be 0 and sum of 1 for ml minus L to plus 1 that will be 2L plus 1. Okay. And sum of ml square from minus L to plus L that will be this much. This is L times L plus 1 times 2L plus 1 over 3. Okay. And similarly you can also write ms instead of ml. So sum of ms will be equal to 0, sum of 1 will be 2s plus 1, sum of ms square will be equal to s into s plus 1 plus, sorry, times 2s plus 1 over 3. You can write. I have written that similar results for ms too. Okay. So now using these results in this equation, what will be our result for m? You can see easily that will be equal to m equal to n mu b square h over 3 kbt times L plus 1 plus 4s times s plus 1. Okay. So this is the expression in this case for magnetization. When you have considered that h nu is much smaller than kBt, it means you are considering that almost all the atoms are in excited state, not in ground state. Okay. So in this case, the magnetic susceptibility chi will be given by m over h. So this h here present will cancel out, and your result for chi is n mu b square over 3 kBt times this much. Okay. Now you can see this factor n mu b square over this much, okay, times this. Here in this case you can see the effective number of Bohr magneton is given by P effective equal to a square root of L times L plus 1 plus 4S times S plus 1. Okay. Actually, you can see this equation 6 also predicts the Curie law. Okay. But the difference appears in the value of PEF. Okay. Effective number of Bohr magneton is actually different from the previous case, but in this case too you can see that this chi is inversely proportional to T. So Curie's law is again obeyed. So this is the result for magnetization and the magnetic susceptibility of a paramagnetic material when you consider that the case that the temperature is very high and field is small. Now in our second part of this lecture we will see the just opposite situation, that what will be magnetization and the magnetic susceptibility of paramagnets when temperature will be small and magnetic field will be large. Okay. So I think you have clearly understand the calculations of this video, and so I will suggest you note down these things in your notebook, and that will be very helpful for your examination purpose. Okay. Thank you very much.